Briefing document. The Entropic Universe Framework. Executive summary. This document synthesizes a comprehensive framework that integrates the search for a theory of everything, TUE, in physics with the universal principles of entropy and the second law of thermodynamics. The central thesis posits that all phenomena in the universe, from quantum fluctuations to the emergence of consciousness and the structure of civilizations, can be understood as manifestations of a single, overarching process: the management and evolution of entropy. The framework begins by addressing the core conflict in modern physics between general relativity and the Standard Model, outlining the leading candidates for a TOE, primarily string theory and loop quantum gravity. It then introduces the second law of thermodynamics as the principle governing the direction of all natural processes, establishing the arrow of time. The core of the synthesis is the philosophical equation, theory of all changes in natural entropy, one nature, which reframes reality itself as a dynamic process of entropic change, rather than a collection of static objects. This integrated lens is then applied hierarchically across multiple disciplines. In biology, life is defined as a transient entropy delay, a complex system that maintains local order by increasing global entropy. In neuroscience, the brain is modeled as a prediction machine that works to reduce information entropy, uncertainty, with consciousness emerging as the pinnacle of this capability. The framework extends to economics, technology, and ethics, analyzing societal structures as metabolic systems that manage energy flows, and proposing an entropic ethics based on intergenerational responsibility. Finally, a detailed case study on Malaysia and University Putra Malaysia, UPM, demonstrates how this framework can be applied to assess and guide sustainable development, conceptualizing a successful society as one that engages in a wise and balanced entropic dance. The foundational conflict in modern physics. The pursuit of a theory of everything is driven by a fundamental incompatibility between the two pillars of modern physics, general relativity and the Standard Model of particle physics. While both are extraordinarily successful in their respective domains, they break down in extreme conditions, such as inside black holes or at the Big Bang. The four fundamental forces physics currently describes the universe as being governed by four fundamental forces. Gravity, the force acting on large scales, planets, galaxies, described by Albert Einstein's theory of general relativity. Electromagnetism, the force governing electricity, magnetism, and light, described by quantum electrodynamics. Strong nuclear force, the force that binds protons and neutrons within atomic nuclei, described by quantum chromodynamics. Weak nuclear force, the force responsible for radioactive decay, described by electroweak theory. The incompatibility of theories. The conflict arises from the disparate nature of the theories governing these forces. General relativity, GR, is a classical deterministic theory that describes gravity as the continuous curvature of spacetime on a macroscopic scale. The Standard Model, SM, is a quantum field theory that describes the other three forces in a probabilistic, discrete framework on a subatomic scale. When attempts are made to quantize gravity, the resulting theory becomes non-renormalizable, losing its predictive power at the ultra-high energies of the Planck scale, approximately 1.222 x 1019 GeV. A TOE is required to provide a quantum description of spacetime and unify these frameworks. Leading candidates for a theory of everything. Two primary theoretical frameworks have emerged as the top candidates for a TOE, each proposing a different fundamental nature of reality. String theory. String theory is the most prominent candidate and posits that the fundamental constituents of the universe are not zero-dimensional points, but one-dimensional strings of an incredibly small size, 10^34. Core idea. Different fundamental particles, electrons, photons, quarks, are simply different vibrational modes of these universal strings, much like a guitar string produces different musical notes. Key achievement. One of the vibrational modes naturally corresponds to the graviton. the hypothetical particle that carries the gravitational force. This is the first framework to seamlessly integrate gravity into a quantum theory. Major challenges: extra dimensions. The theory is only mathematically consistent in a universe with 10 or 11 spacetime dimensions. The extra dimensions are theorized to be compactified or rolled up at a scale too small to observe. Untestability. The energy required to directly observe these strings is far beyond the capacity of any current or conceivable particle accelerator. The landscape problem. The theory allows for an immense number of possible solutions, 500 vacua, each describing a universe with different physical laws, making it difficult to explain why our specific universe exists. Loop quantum gravity, LQG. LQG is the main competitor to string theory, taking a different approach by focusing specifically on quantizing spacetime itself, rather than unifying all forces. Core idea: spacetime is not a smooth, continuous fabric. Instead, it is a discrete network of interconnected loops, or atoms of spacetime. Geometric quantities like area and volume have discrete spectra. Key achievement: LQG successfully resolves the singularity at the Big Bang and inside black holes. It also provides a microscopic derivation of black hole entropy for non-supersymmetric black holes. Major challenges: recovering the classical limit. The theory struggles to consistently show how the smooth spacetime of general relativity emerges at low energies. Incorporating matter. The coupling of standard model particles into the framework is often done in an ad hoc manner and is not derived from first principles. Comparative overview aspect string theory loop, quantum gravity, LQG, fundamental object 1D vibrating strings, spin networks, discrete atoms of spacetime primary goal, unify all forces, including gravity, quantize, general relativity dimensions, requires 10 or 11 spacetime dimensions, works in 4 spacetime dimensions, gravity emerges naturally as a string vibration mode, quantized from the start. Achievements: UV complete quantum gravity, black hole entropy for specific cases, ADS CFT duality, singularity resolution, black hole entropy for general cases, background independence, main weakness landscape of solutions, extra dimensions, lack of testable predictions, difficulty recovering classical limit, ad hoc inclusion of matter, a grand synthesis, integrating TOE and entropy. The framework presented in the source documents proposes a profound synthesis that elevates the concept of entropy to a co-equal status with the search for a TOE. It argues that a complete understanding of the universe requires unifying the rules of physics, TOE, with the direction of reality, entropy. The philosophical equation. Nature, the process of entropy change. The central tenet of this synthesis is the equation, theory of all changes in natural entropy, Asha nature. This is a philosophical statement asserting that the fundamental essence of reality is not static objects, but a dynamic, irreversible process of change governed by the second law of thermodynamics. Everything we observe, from stars to life forms, is a temporary manifestation within this universal flow toward greater entropy. Complementary explanations. TOE and entropy answer different but complementary questions about the universe. Theory, question answered scale, focus theory of everything. What are the fundamental laws governing all interactions? Micro quantum structure, theory of entropy. What is the direction of the universe based on these laws? Macro cosmology, direction of time. A true TOE must not only contain the standard model and general relativity, but also explain why the second law of thermodynamics exists and why the universe began in a state of improbably low entropy. Hierarchical applications of the entropic framework. This unified framework can be applied as a powerful analytical lens across a hierarchy of complex systems, revealing entropy management as a universal principle. Biology and evolution life is framed not as an exception to the second law, but as its most sophisticated manifestation. Life as an entropy machine. A living organism is a system far from thermodynamic equilibrium that maintains its local order and complexity by efficiently consuming low-entropy energy, e.g. sunlight, food, and dissipating high-entropy waste, e.g. heat, into its environment. Evolution as entropy optimization. The process of natural selection can be viewed as a multi-billion-year experiment in discovering more effective strategies for managing energy flows and delaying the inevitable increase in entropy. The evolution of complexity and intelligence represents the development of more advanced tools for this purpose. Neuroscience and consciousness. The framework is applied to the brain and the emergence of consciousness, focusing on the concept of information entropy. The brain as a prediction machine. The brain's primary function is to reduce uncertainty, information entropy, by creating predictive models of the world. It constantly compares sensory input to these models and works to minimize prediction error. Consciousness as entropy reduction. Consciousness is proposed as the pinnacle of this process, the capacity of a highly integrated system to map, model, and influence entropic change in real time. Subjective experience may arise from a system's ability to achieve a transient, complex order, economics, society, and ethics. Human civilization is analyzed as a large-scale metabolic system governed by entropic principles. Entropic economics. Economic activity is fundamentally the transformation of low-entropy natural resources into high-entropy products and waste. This perspective highlights the inherent conflict between models requiring infinite growth and the finite thermodynamic limits of a planetary system. Entropic ethics. This understanding gives rise to a new ethical framework based on concepts like our entropic footprint, intergenerational responsibility for the entropic legacy we leave behind, e.g., climate change, nuclear waste, and the need for a dynamic balance in resource management. Case study: Entropic analysis of development in Malaysia. The framework is applied to the real-world case of Malaysia's national development, providing a quantitative and qualitative assessment of its entropic journey. Malaysia's entropic burden. Malaysia is presented as a microcosm of the challenges faced by rapidly developing nations. Energy profile. The nation's economy is highly dependent on fossil fuels, 90% of primary energy writing, resulting in a significant entropic burden in the form of CO2 emissions, 272 million tons a year, and energy loss. Economic transformation. The shift from a resource-based to an industrial economy has followed a linear take-make-dispose model, creating high levels of solid waste, 38,000 tons a day, and pollution. Ecological impact. Development has led to significant deforestation, loss of 140,000 hectares a year from 1990 to 2020, and river pollution, increasing the entropy of natural ecosystems. The dynamic equilibrium model. The proposed solution is a development philosophy based on achieving a dynamic entropic equilibrium. This principle states that true development is not about reducing local entropy, e.g., building an orderly city, by indiscriminately increasing global entropy, e.g., polluting the atmosphere, but about finding a balance that preserves the integrity of the entire system for future generations. University Putra Malaysia, UPM, as a microcosm UPM, is analyzed as a successful example of an institution managing its entropic journey. Through strategic initiatives, it has demonstrated how to achieve a dynamic balance. Sustainable energy. Installation of 1 MWp of solar capacity, reducing CO2 emissions by 1,800 tons a year. Waste management, a 28% solid waste recycling rate and composting of food waste, creating a more circular system. Innovation and education, research into sustainable technologies and the integration of sustainability into the curriculum contribute to reducing global entropy beyond the campus. UPM's journey proves that an institution can thrive while maintaining ecological integrity, serving as a model for a balanced and ethical national transformation. The ultimate goal is for Malaysia to achieve a successful entropic dance, a state of development that is not mastery over nature, but harmony with its fundamental processes. Entropy and the Quest for a Theory of Everything 1.0. The Great Unanswered Question in Physics. Modern physics stands as one of humanity's greatest intellectual achievements, yet at its heart lies a profound and unresolved conflict. Our understanding of the universe is governed by two extraordinarily successful but fundamentally incompatible theories. On the grandest of scales, Einstein's theory of general relativity describes gravity as the elegant curvature of a continuous and deterministic spacetime, governing the dance of planets, stars, and galaxies. On the most infinitesimal of scales, the standard model of particle physics uses the strange and probabilistic rules of quantum mechanics to describe the other three fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, which command the subatomic realm. Each theory reigns supreme in its own domain, making predictions of astonishing accuracy. But in the universe's most extreme environments, such as the singularity within a black hole or the first moments of the Big Bang, both gravity and quantum effects become overwhelmingly significant. Here, the two pillars of modern physics collide, offering contradictory and nonsensical answers. This incompatibility represents the single greatest unanswered question in science. The quest to resolve it is the search for a theory of everything, TUI, a single coherent framework that unites all four fundamental forces and reveals the ultimate laws of the cosmos. 2.0, the universal constraint, the thermodynamic arrow of time. Before we can explore the candidates for a theory of everything, we must first acknowledge a universal constraint that any such theory must respect and ultimately explain: the second law of thermodynamics. This fundamental principle governs the direction of all natural processes, defining what is known as the arrow of time. It explains why certain events are irreversible, why stars cool, why structures decay, and why we remember the past but not the future. The second law states that the entropy of any isolated system is constantly increasing over time. In essence, systems naturally move from states of order to states of chaos. Entropy is the precise measure of this disorder, randomness, and energy dispersal. Every process that occurs, from the burning of a star to the formation of a galaxy, increases the total entropy of the universe. A powerful metaphor for the ultimate consequence of this law is the concept of heat death, a theoretical future state where all energy differentials have been exhausted and the universe settles into a permanent, stagnant equilibrium, incapable of performing any work. This unyielding march towards disorder is not a secondary phenomenon, it is a core feature of reality. Therefore, a successful theory of everything cannot simply describe particles and forces, it must also explain the origin of the second law. It must account for one of the deepest mysteries in cosmology: why the universe began in a state of extraordinarily low entropy, a highly ordered and statistically improbable condition that allowed for the subsequent emergence of stars, galaxies, and life. The arrow of time, as dictated by entropy, is a non-negotiable feature of our world that must emerge from its most fundamental laws. 3.0, Candidate 1. String theory. The most prominent candidate for a theory of everything is string theory. Its central proposition is a radical departure from previous physics. The fundamental constituents of the universe are not dimensionless points, but infinitesimally small, one-dimensional strings of energy. In this model, the various particles we observe, electrons, photons, quarks, are simply different vibrational modes of these same underlying strings. Much like a single guitar string can produce a variety of distinct musical notes. String theory's most profound achievement is its natural inclusion of gravity. Among the myriad vibrational modes predicted by the theory, one corresponds precisely to the properties of the graviton, the hypothetical quantum particle that carries the gravitational force. This marked the first time a quantum theory was able to produce gravity not as an add-on, but as an intrinsic and necessary component of its mathematical structure. However, this elegance comes at a cost. String theory is only mathematically consistent if the universe possesses 10 or 11 space-time dimensions, rather than the 4, 3 of space, 1 of time, that we perceive. Proponents theorize that these extra dimensions are compactified or curled up on a scale so small they are undetectable. Critically, string theory provides a powerful bridge to thermodynamics through its study of black holes. Using its framework, physicists were able to provide a microscopic derivation of the Bekenstein-Hawking entropy formula, S=A4, where A is the area of the event horizon. By counting the possible string states that could form a specific type of black hole, the theory successfully reproduced the thermodynamic properties that Bekenstein and Hawking had predicted, suggesting a deep connection between gravity, quantum mechanics, and entropy at the most fundamental level. 4.0 Candidate 2 Loop quantum gravity. The primary competitor to string theory is loop quantum gravity, LQG. Rather than attempting to unify all forces at once, LQG takes a more focused approach by quantizing spacetime itself. It challenges one of the core assumptions of general relativity, that spacetime is a smooth, continuous fabric. Instead, LQG posits that spacetime is fundamentally distinct, composed of indivisible atoms of space and time. If we could zoom in to the Planck scale, around 1035 meters, we would find that the fabric of reality is not a single sheet, but a dynamic mesh, a network of interconnected loops known as a spin network. This granular structure of spacetime has profound implications. One of LQG's implications is the resolution of the singularity predicted by general relativity. In the LQG model, the Big Bang is not an infinitely dense point from which the universe emerged, but a big bounce where a previous contracted universe reached a maximum density and rebounded. This resolves the problem of the initial singularity and provides a physical context for the universe's initial low entropy state. Like string theory, LQG has also made significant inroads in understanding black hole thermodynamics. By counting the possible quantum states of the atoms and area on a black hole's event horizon, LQG independently reveals the frequency of
A true TOE must not only contain the laws of thermodynamics, but explain why they must exist. While the fundamental equations of both string theory and LQG are symmetric in time, the universe we inhabit is not. Entropy provides the direction of causality and change, a feature that must arise from the initial conditions of the cosmos, conditions that a TOE must ultimately describe. Gravity in particular serves as a crucial bridge. On one hand, gravity creates organized structures like stars and galaxies, seemingly defying entropy by creating local order. On the other hand, the process of forming these structures and the eventual collapse of matter into black holes generates far more entropy on a global scale. Black hole thermodynamics, as elucidated by both string theory and LQG, reinforces this connection. The Bekenstein-Hawking formula, which equates a black hole's entropy to the surface area of its event horizon, was a key inspiration for the holographic principle. This principle suggests that all the information contained within a volume of space can be described by the physics on its boundary, hinting that space-time itself might be an emergent property of quantum information. This integrated perspective suggests a complementary relationship between the two theoretical frameworks. The theory of everything provides the fundamental laws, the rules of the game, while the theory of entropy describes the large-scale pattern of how the game unfolds over time. Together, They seek to tell the unified narrative of the universe, from a state of perfect symmetry and low entropy at the beginning of time, through the emergence of complex structures and life, toward a final state of maximum entropy and thermal equilibrium. 6.0 Conclusion: the state of the quest. The search for a theory of everything remains the greatest open pursuit in theoretical physics. The two leading candidates, string theory and loop quantum gravity, offer compelling yet incomplete visions of reality. String theory is the only framework that automatically unifies all known forces and particles, including gravity, but it suffers from the challenge of extra dimensions and a vast landscape of possible solutions. Loop quantum gravity provides a fascinating picture of quantum geometry and resolves the singularities that plague general relativity, but has yet to incorporate the matter and forces of the standard model. Despite the formidable challenges, the role of entropy and thermodynamics as a guidepost in this quest has become undeniable. The unyielding arrow of time, the mystery of the universe's initial low entropy state, and the profound connection between gravity and information revealed by black hole entropy are no longer secondary problems. They are central clues that any viable TOE must address. The effort to reconcile the deterministic world of gravity with the probabilistic world of quantum mechanics has revealed that the principles of thermodynamics are not merely emergent statistical laws, but are woven into the very fabric of space-time. Until a final theory makes a clear, testable prediction that is experimentally verified, the ultimate nature of reality will remain a mystery. But it is a mystery in which entropy will continue to serve as an indispensable light, guiding our path toward a deeper understanding of the cosmos. The cosmic quest, in search of the theory of everything. Introduction: the dream of a superpower. Theory: what if all the forces in the universe, from a planet's orbit to the light from your lamp, were all part of one single ultimate rule? This is the grand dream of physicists who are on a quest to find a theory of everything. In simple terms, this is a hypothetical, all-encompassing framework that would unite every fundamental interaction in the universe. The goal is to show that the different forces we observe are all just unique manifestations of one fundamental superpower. To understand this grand quest, we first need to meet the characters of our story, the four fundamental forces that govern everything. 1. The four forces that rule the universe. Modern physics describes our entire universe as being governed by four fundamental forces, the cosmic players whose story we're about to follow. Each has a specific job that shapes reality as we know it. Force name what it does. Its job in the universe. Gravity. The cosmic architect, it shapes planets, stars, and galaxies. Strong nuclear force. The universe's strongest glue. It sticks protons and neutrons together inside the nucleus of an atom. Weak nuclear force. The force responsible for radioactive decay, a process where atomic nuclei change. Electromagnetism. The universal force of light and charge. It powers everything from stars to your smartphone. While scientists understand these four forces well, they are described by two brilliant but deeply incompatible theories, creating a great divide in our understanding of the cosmos. 2. The Great Divide. A tale of two theories. The central reason physicists search for a theory of everything is to solve a huge problem. The two great pillars of modern physics don't work together. Einstein's general relativity. This is the theory for the very large. It elegantly describes gravity as the curvature of space-time. Think of space-time as a smooth, curved sheet of cloth where planets and stars follow the dips and curves. This theory is continuous, no gaps, and deterministic. The past perfectly predicts the future. The standard model of particle physics. This is the theory for the very small. While general relativity handles gravity, the standard model masterfully unites the other three. the strong nuclear, weak nuclear, and electromagnetic forces into a single, elegant quantum framework. It is built on the strange rules of quantum mechanics, which is probabilistic, based on chance, and discrete, comes in chunks or quanta. The big problem is that these two theories, while incredibly precise in their own domains, clash in extreme conditions, inside a black hole or at the very moment of the Big Bang. Both gravity and quantum effects are immensely strong. In these cosmic laboratories, the rules of general relativity and the standard model break down, giving nonsensical answers. For physicists, this isn't just a mathematical problem, it's a cosmic puzzle. Nature is telling us that our most successful ideas are missing a crucial piece, and the universe has a deeper, more elegant secret to reveal. This is the central cliffhanger of modern physics. To bridge this great divide, physicists have developed incredible new ideas, with two rival heroes vying to resolve the conflict and become the theory of everything. 3. The top contenders, dueling ideas of unified physics. 3.1. String theory, the universe as a symphony. String theory is the most popular candidate for a theory of everything. Its core idea is revolutionary. Fundamental particles like electrons and protons are not zero-dimensional points, but tiny, one-dimensional vibrating strings, or ropes. The theory works like this. Just as guitar strings can produce different notes, one type of basic string can vibrate in different ways to become all the different particles we see. A string vibrating one way is an electron, another way a photon, and so on. Then, in a stunning breakthrough, physicists discovered something completely unexpected hidden in the mathematics. One of the string's natural vibration modes behaved exactly like the graviton, the hypothetical particle that carries the force of gravity. This was the first time gravity appeared naturally within a quantum theory, offering a potential path to unification. However, string theory faces several major challenges. Extra dimensions. The theory is only mathematically consistent if the universe has 10 or 11 dimensions, not the 4, 3 of space, 1 of time, that we experience.
Physicists believe the extra dimensions are rolled up or compacted on a scale so small we can never perceive them. Think of a garden hose or a tightly rolled up straw. From far away, it looks like a one-dimensional line. But up close, you can see its true, three-dimensional circular shape. String theory suggests the extra dimensions are rolled up so tightly that they are only visible at the unimaginably tiny scale of the strings themselves. Untestable for now. The energy required to see these tiny strings is trillions of times greater than what our most powerful particle accelerators can produce. This is a major criticism, as scientific theories must be testable to be validated. Too many answers. String theory doesn't produce just one answer. It allows for billions of possible mathematical solutions, each describing a universe with slightly different physical laws. This is known as the landscape problem, and it makes it incredibly difficult to find the single solution that describes our universe. 3.2. Loop quantum gravity, weaving the fabric of space-time. Loop quantum gravity, LQG, is string theory's main competitor, and it takes a completely different approach. Instead of trying to unify all the forces, LQG focuses on quantizing space-time itself. Here's a helpful analogy to understand the difference. In general relativity, space-time is like a smooth, continuous sheet of cloth. In loop quantum gravity, space-time is like a network of interconnected threads, loops. The fabric of the universe is actually a fine mesh made of tiny, discrete loops. LQG has had some key successes. It has helped explain some properties of black holes, and most importantly, it resolves the singularity at the Big Bang, offering a picture of the universe's beginning without the nonsensical infinities predicted by other theories. Its primary challenge, however, is that it has not yet managed to elegantly combine the particles of the standard model into its framework. With such different and fascinating approaches, it's helpful to see how these two theories stack up side by side. 4. A quick comparison. Strings versus loops.
This table breaks down the core differences between the two leading theories. Aspect string theory, loop, quantum gravity core idea. Fundamental particles are tiny, vibrating one-dimensional strings. Space-time itself is made of discrete, indivisible chunks or loops. Approach to gravity starts by unifying all particles and forces and finds gravity naturally emerging as a vibration of a string. Starts by directly quantizing space-time itself, weaving gravity into the quantum fabric of the universe from the beginning. Required dimensions 10 or 11 dimensions. The 4 dimensions we experience, 3 space plus 1 time. A key appeal of loop quantum gravity for some physicists is that it doesn't require extra unobserved dimensions to make its math work, unlike string theory. While these theories compete, the quest itself pushes science forward, with the final answer remaining the greatest unsolved mystery in physics. 5. The quest continues, the unsolved mystery. Today, a confirmed theory of everything remains the greatest open ticket in theoretical physics. The search is far from over, and it's not just happening on chalkboards. Scientists are actively looking for clues from the cosmos itself, studying gravitational waves from colliding black holes and analyzing the cosmic microwave background, the faint leftover glow from the Big Bang, for any hint that might point them in the right direction. The quest continues, not just for an equation, but for the true identity of that single superpower from which all of reality springs. It's an attempt to answer the most fundamental questions we can ask. Where did we come from, and where are we going?
The search for a theory of everything is a testament to boundless human curiosity and our profound desire to understand our place in the universe. A proposal for research into the interplay of entropic principles and fundamental physical laws. 1.0 Introduction and Problem Statement. Modern physics is founded upon two remarkably successful, yet profoundly incompatible, theoretical pillars. On one hand, Einstein's general relativity, GR, provides a deterministic and continuous description of gravity as the curvature of space-time on a macroscopic scale. On the other, the Standard Model, SM, of particle physics offers a probabilistic and discrete quantum framework for the electromagnetic, strong nuclear, and weak nuclear forces that govern the subatomic realm. These theories are precise in their respective domains, but they collide under the universe's most extreme conditions, such as the interiors of black holes and the moment of the Big Bang, where both gravitational and quantum effects are significant. Resolving this central schism is paramount to achieving a complete understanding of the cosmos. This research project will address two core problems that lie at the heart of this theoretical impasse. 1. The unification problem. The primary challenge is to synthesize the descriptions of the 4 fundamental forces into a single, coherent mathematical framework, a theory of everything, TOE. Such a theory must reconcile the classical continuous nature of general relativity with the quantum probabilistic nature of the Standard Model, providing a unified explanation for all physical interactions. 2. The thermodynamic problem. A parallel and equally fundamental challenge is to explain the origin of the second law of thermodynamics from first principles. Specifically, any complete theory of the universe must account for the thermodynamic arrow of time, the irreversible increase of entropy, disorder, in isolated systems, and provide a non-arbitrary explanation for the universe's highly ordered, low-entropy initial state, often referred to as the past hypothesis. The central thesis of this research is that a viable theory of everything must do more than unify the fundamental forces. It must also intrinsically explain the universe's entropic properties. A theory that successfully describes the fundamental rules of the game must also explain the direction in which the game is played. This project will therefore conduct a rigorous theoretical investigation into the relationship between the leading candidates for a TOE and the foundational principles of thermodynamics and information theory. By examining how these frameworks treat concepts of time, information, and order, this research seeks to establish thermodynamic consistency as a critical constraint for any ultimate physical theory. 2.0 Theoretical Framework and Literature Review. To fully appreciate the research gap this project aims to fill, it is essential to review the two dominant but incompatible pillars of modern physics, the leading candidates for their unification, and the thermodynamic principles that a final theory must ultimately explain. This review establishes the context for our central research questions by outlining what is known, what is hypothesized, and what remains fundamentally unresolved. 2.1 The foundational incompatibility of general relativity and the Standard Model. General relativity and the Standard Model are triumphs of 20th century physics, yet their core assumptions and mathematical structures are fundamentally at odds. Their incompatibility becomes acute at the Planck scale, MP under HCG 1.22 x 1019 GeV, where a unified theory of quantum gravity is required to make sensible predictions. The table below summarizes their core distinctions. General relativity, GR, Standard Model, SM, domain, gravity, and the large-scale structure of the cosmos, planets, galaxies, the universe. Domain, the electromagnetic, strong nuclear, and weak nuclear forces governing the subatomic world of particles. Fundamental nature, a classical field theory. Space-time geometry is deterministic and continuous.
Fundamental nature, a quantum field theory. Particle interactions are probabilistic and discrete, quantized. Treatment of spacetime. Spacetime is dynamic and curved by mass and energy. It is the fabric of reality. Treatment of spacetime assumes a fixed flat background spacetime on which quantum fields operate. 2.2 Leading. 2E Candidate, String Theory. String theory is currently the most popular candidate for a theory of everything. Its central premise is a radical departure from the Standard Model's conception of elementary particles. Core idea: fundamental entities are not zero-dimensional points, but one-dimensional, vibrating strings of a characteristic size of approximately 10 to 34 meters. Different particles, e.g., electrons, photons, quarks, are merely different vibrational modes of the same underlying string, much like different musical notes are produced by different vibrations of a guitar string. Primary achievement: the theory's most significant successes are rooted in its ability to connect gravity with quantum mechanics. One of the string's natural vibrational modes corresponds precisely to the properties of the graviton, the spin 2 particle that mediates the gravitational force. This marked the first time a quantum theory had naturally and necessarily incorporated gravity. It provides a microscopic derivation of the Bekenstein-Hawking entropy for a large class of extreme black holes, Strominger-Vafa 1996, directly linking string states to a core formula in gravitational thermodynamics. Significant challenges: extra dimensions. String theory is only mathematically consistent in a universe with 10 or 11 spacetime dimensions. The unobserved dimensions are hypothesized to be compactified or rolled up on an incredibly small scale. The landscape problem. The theory permits a vast number of possible solutions, at least 10,500, each describing a universe with potentially different physical laws. This makes it exceedingly difficult to identify the unique solution that describes our specific universe. Where geometric operators like area have discrete spectra. For example, the area operator has minimum values given by the formula dA
Key successes. LQG has achieved notable results in general relativity extent. It mathematically resolves the singularity tends to increase over time. This principle provides the arrow of time, distinguishing the past from the future, and raises one of the deepest mysteries in cosmology. The universe began in a highly ordered, exceptionally low entropy state.
Any fundamental theory must ultimately explain this initial condition. The discovery of Bekenstein-Hawking entropy, which relates the entropy of a black hole directly to the surface area of its event horizon, SBH or eta4LP2, provides a critical bridge. This formula profoundly connects gravity, the geometry of spacetime, A, and thermodynamics, entropy, S, because entropy is fundamentally a measure of information, in this case, the information hidden by the event horizon. Therefore, a successful 2E cannot treat this formula as a mere curiosity. It must emerge as a direct consequence of the theory's fundamental postulates, thereby proving the theory's thermodynamic, not just quantum gravitational, completeness. 3.0 Core Research Questions. Based on the theoretical gaps and conceptual links identified in the preceding review, this research project will pursue 3 specific guiding questions aimed at synthesizing the frameworks of fundamental forces and entropic dynamics. The central inquiry is not merely if a TOE can accommodate thermodynamics, but how the principles of thermodynamics might emerge directly from the TOE's foundational structure. 3. Emergence from first principles. How might the second law of thermodynamics and the arrow of time arise directly from the fundamental mathematical structures and postulates of string theory and loop quantum gravity, respectively? 4. The initial state problem. To what degree can the cosmological models derived from string theory, e.g., the landscape of vacua, or loop quantum gravity, e.g., the Big Bounce, provide a non-arbitrary physical explanation for the universe's initial low entropy state? 5. Gravity as the thermodynamic bridge. What are the specific mechanisms within each TOE candidate that quantitatively connect the geometry of spacetime to thermodynamic properties, particularly in unifying the microscopic statistical description, e.g., string states, spin networks, with the macroscopic Bekenstein-Hawking entropy of black holes? These questions will guide a systematic exploration of the entropic frontier in fundamental physics. 4.0 Research Methodology. This investigation will be purely theoretical in nature, employing a multi-stage comparative analysis of the mathematical formalisms and philosophical underpinnings of the primary TOE candidates. The methodology is designed to systematically address the core research questions by dissecting each theory's treatment of information, state evolution, and cosmology. 4.1 Phase 1 Comparative Theoretical Analysis. The first phase will consist of a rigorous comparative study of the formalisms within string theory and loop quantum gravity. This analysis will move beyond a surface-level comparison to deconstruct how each theory treats fundamental concepts such as information, degrees of freedom, the nature of a physical state, and the evolution of those states. The primary objective is to identify mathematical structures and conceptual homologies within each framework that align with the principles of statistical mechanics and information theory. This will lay the groundwork for understanding how thermodynamic behavior, like the tendency toward equilibrium, might be an emergent property of the underlying quantum geometry or string dynamics.
4.2 Phase 2 Cosmological Model Synthesis. The second phase will synthesize the cosmological predictions of each framework, specifically string cosmology and loop quantum cosmology, with the established observational fact of a low entropy Big Bang pre-past hypothesis. The analysis will critically evaluate which theory provides a more natural, less fine-tuned explanation for these initial conditions. The assessment will focus on the capacity of each model to explain why the universe began in such a highly ordered state, rather than simply positing it as an arbitrary boundary condition. This involves examining mechanisms like the Big Bounce in LPG, or selection principles within the landscape of string theory.
4.3 Phase 3 Philosophical Inquiry. The final phase of the research will explore the profound philosophical implications that stem from each framework's relationship with entropy. Building on the findings from the first two phases, this inquiry will investigate how each theory informs foundational questions regarding the nature of time, the conflict between determinism and probability in physical law, and the physical principles that allow for the emergence of complex, ordered structures like life in an overwhelmingly entropic universe. This analysis will connect the abstract mathematics of each theory to its broader implications for our understanding of reality. 5.0 Expected Contributions and Significance. By systematically investigating the intersection of quantum gravity and thermodynamics, this project is poised to make significant and novel contributions to both theoretical physics and the philosophy of science. The research moves beyond the singular goal of force unification to demand a more holistic and physically complete theory of everything. The expected contributions of this project include new constraints on fundamental theories. By demanding thermodynamic consistency as a core requirement, this research aims to identify new theoretical constraints on 2E candidates. This approach could highlight previously overlooked weaknesses in a theory or suggest novel directions for development, helping to prune the vast landscape of theoretical possibilities. A grounded explanation for the arrow of time. The project seeks to elevate the explanation for the second law of thermodynamics from a posited initial condition, the past hypothesis, to a derived consequence of a more fundamental physical law. Success in this area would provide a more complete and satisfying scientific worldview, explaining not just the rules of the universe, but also the direction of its narrative, informing foundational philosophical debates. This research will provide a rigorous, physically grounded analysis to advance philosophical debates on the nature of reality. It will link abstract concepts such as the essence of time, causality, and the emergence of order from chaos directly to the leading mathematical frameworks of modern physics, providing a concrete basis for what have often been purely metaphysical discussions. Ultimately, a theory that quantizes gravity without explaining the thermodynamic arrow of time describes a universe of cosmic architecture but no history. This research is a necessary step towards a truly complete theory, one that explains not just the story, but the irreversible play that unfolds from it. A grand unification, understanding the theory of everything, the quest for a superpower theory. The search for a theory of everything, 2E, stands as the ultimate quest in physics. It represents the final chapter in a story that began with Newton, a profound human ambition to reach the universe's ultimate meaning. It is an attempt to create a single, all-encompassing framework and describe every fundamental interaction in the universe. In simple terms, a theory of everything aims to show that all diverse forces will exist, from the colossal pull of gravity that holds galaxies together to the subatomic forces that govern the atom, are merely different manifestations of one fundamental superpower. This grand unification will provide a single set of equations to explain all of physical reality. 2. The universe's four ruling forces. Modern physics currently describes the universe as being governed by four distinct fundamental forces. Understanding these forces is the first step toward understanding the effort to unite them. Gravity. This is the force that acts on a massive scale, governing the motion of planets, stars, and entire galaxies. Electromagnetism. This force controls the phenomena of electricity, magnetism, and light. Strong nuclear force. This is the incredibly powerful force that binds protons and neutrons together within the nucleus of an atom. Weak nuclear force. This force is responsible for the process of radioactive decay, where atomic nuclei change their composition. While we have incredibly accurate theories for these forces, a deep conflict exists between the theory for gravity and the theory for the other three, creating the central challenge that a theory of everything must solve. 3. The Great Divide, a tale of two theories. The big problem in modern physics is the profound incompatibility between our two most successful theories, general relativity, which describes gravity, and quantum mechanics, which underpins the standard model of particle physics for the other three forces. They describe the universe in fundamentally different ways. General relativity, the macro world, quantum mechanics, the micro world, governs the universe on the largest scales, describing planets, galaxies, and black holes. Governs the universe on the smallest scales, describing the subatomic world of particles. It is a continuous and deterministic theory, where space-time is a smooth fabric and outcomes can be precisely calculated. It is a discrete and probabilistic theory, where energy exists in distinct packets and outcomes are based on probabilities. This incompatibility becomes a critical issue under extreme conditions, such as those inside a black hole or at the very moment of the Big Bang. In these scenarios, general relativity treats space-time as a smooth, continuous fabric, while quantum mechanics requires the universe to be pixelated and probabilistic at the smallest scales. When gravity becomes so strong that the fabric of space-time itself would need a quantum description, our current theories simply break down. Physicists need a theory of everything to bridge this divide and explain what happens when these two worlds collide. 4. Top candidates for unification. The monumental challenge of unification has spurred physicists to explore several radical and often competing ideas. These two frontrunners attack the problem from opposite ends. String theory aims to explain all particles and forces from which space-time emerges, while loop quantum gravity starts by building a quantum theory of space-time itself, hoping to fit the particles in later. 4.1. String theory, cosmic guitar strings. The core idea of string theory is that the fundamental building blocks of the universe, particles like electrons and photons, are not zero-dimensional points. Instead, they are unimaginably small, one-dimensional vibrating ropes or strings. This simple premise has a profound consequence. Just as a single guitar string can produce different musical notes by vibrating in different ways, one single type of fundamental string can vibrate in different modes to appear as all the different particles we see. The most significant achievement of string theory is that one of its vibration modes naturally behaves like the graviton, a hypothetical particle thought to follow the force of gravity. This was the first time gravity emerged naturally in quantum theory, offering a powerful hint that it might be on the right track. However, the theory faces major hurdles. Extra dimensions. String theory is only mathematically consistent if the universe has 10 or 11 dimensions, rather than the 4, 3 of space, 1 of time, that we experience. Currently untestable. The energy required to see these tiny strings is vastly beyond the reach of any particle accelerator we can build, making the theory difficult to prove or disprove. The landscape problem. The theory allows for billions of possible mathematical solutions, each describing a universe with different physical laws, making it hard to find the one that describes ours. 4.2. Loop quantum gravity, weaving the fabric of space-time. Loop quantum gravity, LQG, is string theory's main competitor and takes a fundamentally different approach. Instead of unifying forces, LQG focuses on quantizing space-time itself. It suggests that the fabric of space-time is not smooth and continuous, but is made of discrete, indivisible atoms of space. This idea can be understood using a simple fabric analogy. General relativity, space-time is like a smooth, curved sheet of cloth. Loop quantum gravity. Space-time is like a mesh of tiny interconnected loops or threads. In this view, if you could zoom in on reality to the smallest possible level, you wouldn't see a smooth location, but a shimmering, indivisible pixel of space connected to its neighbors. LQG has had success in explaining some properties of black holes and resolving the singularity at the Big Bang, but it currently struggles to elegantly incorporate the particles and forces described by the Standard Model. 5. A head-to-head comparison. The two leading theories offer distinct paths toward unification, each with its own compelling strengths and significant challenges. Feature string theory, loop quantum gravity, LQG, core idea. Fundamental particles are tiny, vibrating one-dimensional strings. Space-time itself is not continuous, but made of discrete atoms or loops. Primary strength. Naturally incorporates gravity as one of the string's vibration modes. Resolves singularities at the Big Bang and in black holes. Biggest challenge, requires extra, unobserved dimensions, and has a landscape of too many possible solutions. Has not yet successfully incorporated the particles from the Standard Model in an elegant way. With string theory offering a universe of particles, and loop quantum gravity weaving the universe's fabric, physicists stand at a crossroads, pondering which path leads to the ultimate reality. 6. Conclusion. The greatest open ticket in physics. The quest for a theory of everything remains one of the most exciting and challenging frontiers in science. A true TOE must not only provide a quantum description of space-time, but also successfully reproduce the predictions of both the Standard Model and general relativity in their respective domains. String theory's genius is that gravity simply falls out of its mathematics, a stunning achievement. Yet it comes at a cost, a landscape of billions of possible universes with no clear way to find our own. Loop quantum gravity offers a compelling picture of quantum geometry and resolves cosmic singularities, but it has yet to successfully integrate the other known forces. Until one of these frameworks, or an entirely new one, makes a clear, testable prediction that is verified by experiment, the theory of everything remains the greatest open ticket in theoretical physics. 6. Mind-bending ideas. From the quest to find the theory of everything, modern science has pulled back the curtain on much of the universe's machinery, yet at the very heart of our understanding lies a schism, a civil war in physics. Our two most celebrated theories about reality, one for the vast cosmos and one for the quantum realm, run on fundamentally incompatible operating systems. It's a universe destined to crash. This incompatibility isn't a minor detail, it is the single biggest problem in physics today. The theory of everything is the name for the ultimate quest to resolve this conflict, to find a single, elegant framework that describes all of reality. The search has forced scientists to question everything we thought we knew about space, time, and matter. The leading ideas are more surprising and counterintuitive than any science fiction. Here are 6 of the most mind-bending clues from that grand mystery. 1. Our 2 best theories of the universe. Don't talk to each other. The central conflict in physics is between 2 titans. The first is Albert Einstein's general relativity, which is like classical music, a grand, sweeping, and perfectly predictable symphony of space-time. It governs planets, galaxies, black holes, and the very fabric of the cosmos. The second is the Standard Model of particle physics, which is like jazz, a frenetic, improvisational, and probabilistic jam session of particles and forces in the subatomic world. The theories don't just use different instruments, they speak fundamentally different languages. General relativity is deterministic and describes a smooth, continuous reality. The Standard Model is probabilistic and describes a world of discrete, quantized units. In their own domains, both are incredibly precise. But when you try to use them together, in extreme conditions like the singularity inside a black hole, or at the moment of the Big Bang, where both gravity and quantum effects are immensely strong, the math shatters. They give nonsensical answers. This fundamental clash is why a theory of everything is not just a scientific luxury, but a necessity. 2. Everything is made of tiny, vibrating strings. The first major clue in this quest came from an unexpected source. String theory, perhaps the most famous candidate for a theory of everything, proposes a core idea that is both simple and radical. The fundamental building blocks of reality are not zero-dimensional points, but tiny one-dimensional vibrating strings, or ropes, on the order of 1035 meters. Everything we see, electrons, quarks, photons, is just a different manifestation of these basic strings. The concept is best understood through an analogy. Just as a single guitar string can produce different musical notes by vibrating in different ways, a single fundamental string can become different particles by vibrating in different modes. An electron is a string vibrating one way, a photon is the same string vibrating another way, and so on. All the particles and forces in the universe are just the different songs played by these fundamental strings. 3. Gravity isn't a fundamental force, it's just one of the strings of songs. This is arguably the most stunning and impactful achievement of string theory. For decades, gravity has been a immovable obstacle, the one force that refused to fit into any quantum theory. Physicists' previous attempts to force it had failed spectacularly. Then, as scientists explored the mathematics of string theory, something miraculous happened. They didn't have to awkwardly shoehorn gravity into the theory. Instead, they discovered that one of the natural vibration modes of the string had the exact properties of the graviton. Hypothetical particle that carries the force of gravity. It just appeared in the equations on the plane. The miracle of string theory was that the solution, the graviton, emerged from the mathematics not as a target, but as an unavoidable consequence. This is the first time gravity has appeared naturally in quantum theory. This is profoundly important because it elegantly unifies gravity with the quantum world under a single theoretical roof. The force that holds galaxies together and the forces that govern the atom are, in this view, generated by the same underlying object. This is the primary goal of a theory of everything. For our universe hides at least 6 extra dimensions. One of the most counterintuitive requirements of string theory is that it doesn't work in the universe we think we know. For the theory's mathematics to be consistent, the universe can't have just the 4 dimensions we experience, 3 of space and 1 of time. It must have 10 or 11 space-time dimensions. So where are they? The proposed solution is that these extra dimensions are compacted or rolled up into a shape so infinitesimally small that we cannot perceive them. They exist at every point in space, but are curled up on a scale far smaller than an atom, hidden from our senses and our most powerful instruments. However, this elegance comes at a steep price. String theory faces 2 major challenges that keep it in the realm of the hypothetical. First, it is currently untestable. The energy required to see these strings is far beyond anything we can build. Second, it suffers from the landscape problem. The mathematics allows for billions of possible solutions, each describing a universe with different physical laws. This makes it incredibly difficult to pinpoint the one version that describes our specific universe. 5. Space-time might be a pixelated fabric, not a smooth sheet. But another group of physicists decided to attack the problem from a completely different angle. Instead of starting with particles and forces, loop quantum gravity, LQG, focuses on quantizing spacetime itself. It proposes that the fabric of spacetime is not a continuous smooth sheet, but is made of discrete, indivisible units, like atoms of spacetime. A simple analogy clarifies the difference. General relativity. Spacetime is like a smooth, curved sheet of cloth. You can zoom in forever, and it will always be smooth. Loop quantum gravity. Spacetime is like a network of interconnected threads or loops. If you zoom in far enough, you'll see that the fabric is actually a fine mesh made of tiny, indivisible loops. This approach yields a major triumph. It resolves the problem of the Big Bang singularity. In LQG, the universe doesn't begin from an infinitely dense point.
Instead, it may have emerged from the collapse of a previous universe in a big bounce. However, LQG has its own primary weakness. While it provides a compelling picture of quantum spacetime, it still has not managed to combine the particles of the standard model in an elegant way. This presents a fascinating trade-off for physicists. String theory elegantly unites particles and forces, but requires untestable extra dimensions, while LQG provides a concrete, pixelated spacetime, but struggles to incorporate the particles that live within it. 6. Order, life, and you are not miracles. You're engines of chaos. Beyond the unification of forces, any complete theory must also explain a more universal and mysterious feature of our cosmos: the relentless forward march of time, driven by a law known as entropy. The second law of thermodynamics states that the total entropy or disorder in the universe is always increasing. This gives us the arrow of time and explains why things break but don't spontaneously reassemble. At first glance, complex structures like stars, galaxies, and life itself seem to defy this law by creating local pockets of incredible order. But the counterintuitive truth is that these structures do not fight against entropy. They are a consequence of it. Life achieves its own complex order by becoming incredibly efficient at increasing the total entropy of the universe. It takes in low entropy energy, like sunlight, and exports high entropy waste, like heat, maintaining its own structure by accelerating chaos in its environment. Every living organism is a highly efficient entropy waste machine. It maintains its own local order by bringing entropy into its environment. Conclusion: the greatest open ticket in physics. The quest for the theory of everything remains the greatest open ticket in theoretical physics. While string theory and loop quantum gravity are the leading contenders, other intriguing ideas like asymptotic safety and causal dynamical triangulations will also explain the fundamental nature of the universe from different angles. Any true theory of everything must do more than just unite the forces of nature. It must also explain the deepest properties of our reality, from the fabric of space-time to the inexorable arrow of time. The final theory will do more than write the rules for stars and strings. It will provide the ultimate canvas on which our own existence is painted. Will that canvas reveal a universe of predetermined artwork, or one where the beautiful, chaotic dance of life and consciousness was an inevitable masterwork? Have you ever looked up at the night sky and wondered how it all works? For centuries, physicists have searched for a single elegant idea, a master equation that could describe everything in the universe, from quarks to galaxies. This dream isn't just about science, it's about our deep desire to understand our place in the cosmos. We see patterns everywhere: the seasons, the rising sun, an apple falling, the moon's orbit, all following fundamental rules. Science has shown us the universe is governed by laws, not chaos. But here's the puzzle. We've found several sets of laws, and they don't always fit together. Imagine having a car manual and a computer manual, both brilliant but written in different languages. That's modern physics. One set of rules for the very big, another for the very small. The ultimate goal? To find the universe's source code, the original language from which all other instructions are derived. This journey to a theory of everything pushes the boundaries of imagination and technology. It's about unification, seeing the deep connections beneath the complexity of our world. And as we'll see, this story isn't just about forces and particles. It's about the one principle that might govern all change, from the birth of stars to the choices we make. Let's begin the search for that unifying idea. To understand this quest, we need to meet the universe's main characters, the four fundamental forces. First, gravity, the force that keeps us grounded and holds planets in orbit. Next, electromagnetism, the reason we see, the force behind light, electricity, and chemistry. Then, the strong nuclear force, binding protons and neutrons in the atomic nucleus, the glue at the heart of matter. And finally, the weak nuclear force, responsible for radioactive decay and crucial for the sun's fusion. These four forces write the story of the universe. But there's a catch. Gravity stands apart, refusing to fit neatly with the others in a single mathematical framework. We have one set of rules for the cosmic scale, another for the quantum world. The challenge is to unite them, to find the common thread. Why do these forces exist, and why do they have the strengths they do? The answer could reveal the universe's deepest secrets. The search for unity is the search for the universe's true operating system. And it's a journey that takes us to the frontiers of physics. Let's see where it leads.
How do we unite these forces? Two leading ideas have emerged: string theory and loop quantum gravity. String theory imagines every particle as a tiny, vibrating string. Different vibrations create different particles, like musical notes on a cosmic instrument. This elegant idea could unify all forces, but it requires extra dimensions, 10 or 11 in total, curled up beyond our perception. Testing this is a huge challenge. Loop quantum gravity takes a different path. It says space itself is made of tiny, indivisible chunks, like pixels in a digital image. Gravity, in this view, emerges from the geometry of these quantum loops. Both theories aim to describe gravity in the quantum language of the subatomic world. Both are bold, beautiful, and unproven. The quest for a unified theory is a journey into the unknown. It's about finding the rules that govern everything, from the smallest particles to the largest galaxies. But what if there's another principle at work, one that underlies even these fundamental forces? To find out, we need to look at a law that governs all change, the second law of thermodynamics. Enter entropy.
Beyond the search for unified forces, there's a law that shapes everything, the second law of thermodynamics, centered on entropy. Entropy measures disorder. The second law says entropy in an isolated system never decreases. It only stays the same or increases. This simple rule explains why things happen. Hot coffee cools, never heats up on its own. An egg scrambles, but never unscrambles. The universe moves from order to disorder. This is the arrow of time. The Big Bang began with incredibly low entropy. Since then, the universe has expanded, cooled, and grown more disordered. Stars burn out, galaxies drift apart, energy spreads. The journey toward maximum entropy, sometimes called the heat death, is the universe's ultimate fate. But this isn't just a story of decay. The flow from low to high entropy powers everything: the sun, life, and all complexity. Entropy's increase is the engine of creation, not just destruction. It drives change, fuels life, and shapes the cosmos. The second law is the universe's most relentless rule. It's the reason anything happens at all, and it might be the key to understanding everything.
What if the search for a unified theory is deeply connected to entropy? The entropic principle suggests the universe is always finding ways to increase disorder as efficiently as possible. Forces and particles may be the universe's tools for maximizing entropy. Gravity, for example, forms stars, engines that turn ordered fuel into disordered heat and light. The laws of physics might exist because they're the best way to move the universe from low to high entropy. The universe isn't just following rules, it's actively seeking the fastest path to disorder, creating complexity along the way. Any true theory of everything must explain not just the forces, but why they lead to a universe so good at creating disorder.
If the universe trends toward disorder, what is life? Life is a local island of order, accelerating entropy in its environment. Plants use sunlight to build complex molecules, but in living and dying, they turn ordered energy into disordered heat. We eat, breathe, and think. Each process increases entropy. Our brains burn energy to create mental order, but release heat in the process. Societies and economies do the same.
They create order locally by increasing global disorder. The challenge is to manage this process wisely, creating well-being without overwhelming the environment. Life doesn't defy the second law, it serves it, making the river of entropy flow faster. Our task is to balance creation and destruction, order and disorder. That's the heart of sustainable progress. How can a nation create prosperity without causing runaway disorder? Malaysia's story is a case in point. Growth powered by natural resources brought wealth, but also environmental costs, the entropy tax. The challenge: maximize societal order, health, education, well-being, while minimizing entropy production, pollution, depletion. Malaysia is shifting to a knowledge-based, high-tech economy, aiming for more value with less entropic cost. Investments in renewables like solar and biomass are part of this conscious effort. The goal balances societal progress with environmental stability. Sustainable development means being smarter with our entropic budget. It's about building a future that lasts. Universities are engines of a knowledge-based economy, entropy battling systems. At UPM, research in sustainable agriculture and resource management aims to produce more with less, minimizing environmental cost. The university's expansion into engineering, biotech, and environmental science reflects a broader entropic challenge. From efficient solar cells to circular economies, UPM is a catalyst for sustainable growth. Institutions like UPM are critical infrastructure for a balanced future. They teach us to manage entropy wisely, building prosperity without overwhelming the planet. Investing in education and research is investing in resilience. It's how we ensure well-being doesn't come at the Earth's expense. We began with the universe's deepest questions and ended with the challenge of building a sustainable world. The second law of thermodynamics connects the fate of stars to the fate of our civilization. Life, consciousness, and society are beautiful, temporary structures of order in a universe flowing toward disorder. Our choices matter. They shape the rate and nature of entropy production on Earth. True progress is measured by efficiency, creating well-being, knowledge, and fairness for the least entropic cost. By understanding our place in the entropic flow, we can make wiser choices. We can build a future that's prosperous, resilient, and fair. The laws of physics set the rules, but we shape the outcome. We can learn to surf the wave of entropy, creating a civilization that's both creative and responsible. The future is uncertain, but it's ours to shape.